Not existing. Oh, you trust my voice?
What I would like to talk about on that sheet of line paper is that I just want to kind of review, and for some of us this isn't that big of a deal, but for some of us this is a big deal. So as I was trying to mark the major entities thing yesterday, and it seemed like a lot of people were getting really confused between ionization, dissociation, and major entities. So I just want to clear that up a little bit. So at the top of your page, I would like you to write major entities review. And what I want to ask you is that there's, in general, like 4 different types of compounds out there, or 4 different types of substances, I should say. There's elements, and then give like a tiny little bit of space, maybe 1 or 2 lines. What's another type of substance out there? A compound, there's lots of different compounds though, so let's be specific. We could say an ionic compound. We could say a molecular compound. And then the very last one, Luke, is what? Acids.
What bases?
Now, bases, as far as you're concerned right now, bases will always be an ionic compound. They're always ionic. So we can just treat them like ionic compounds. If you see a base, like, for example, you don't write this down, but if you see a base, potassium hydroxide, right? All bases have to be ionic hydroxides. So you just treat it like any other regular ionic compound for now. That's okay. Okay, let's try and think about these. Of these 4 things, which ones have the potential to be able to split up? Which ones have the ability to go from a substance and split off into ions? Ionic compounds for sure, right? So beside ionic compounds, you could say can split up. What else in this list has the ability to split up? Acids, right? So they can split up. So elements will never split up. Elements, if I said, for example, if I had a tube of copper, right, because copper is often used for plumbing, when I take that tube of copper and when I dump it into a lake, not that I ever would, but when I toss that tube of copper into a lake, does it all of a sudden start to dissolve and turn into ions and stuff like that? No, so these ions, or so these elements, they are always low solubility, and they are always atoms. Elements are never ions. If I said you had a chunk of iron, is it iron with no charge, or is it iron 2 plus or iron 3 plus? Which one is it going to be? It's iron with no charge at all. They're always atoms. If I said you have oxygen gas, what's the charge on oxygen gas? 0. Nothing, because it's an element. It's like in its pure form, that kind of thing. Ionic compounds, when we're doing major entities, we want to say, okay, well, there's 2 different types, right? What are the 2? Low what? Low solubility and high solubility, right? So when we have low solubility, can low solubility ionic compounds split up? Do they have the ability?
No.
Okay. For the most part, no. off to the side or down at the bottom, somewhere where you have a little bit of room, I want you to draw an ionic compound. Just, you know, a small amount of it. This is an ionic compound. It's repeating positive, negative, positive, negative, positive, negative, positive, negative. When I put this into water, even if it's low solubility, a tiny itty bitty little bit of it will dissolve, okay? So most of it, if it's low solubility, stays together. But some of the ions will be able to split up. Now what happened? Did the majority of this ionic compound dissolve? No, the majority of it didn't. But did some of it dissolve? Yes, some of it did. So low solubility, the major entity, you just write it as it is, okay? So for the major entity and for a low solubility compound, you just keep together as your ionic compound. For high solubility, does any of it stick together? No, it all dissolves. It all splits up. So you have to split it up. You have to dissociate it. But we will say for now, split it up. When I write a dissociation equation for an ionic compound, I just want to say this. When I write a dissociation equation for an ionic compound, it doesn't matter if it's high solubility or low solubility. In a low solubility ionic compound, will some of it split off? Will some of it dissolve and break apart? Yeah, even in low solubility. Low doesn't mean none. Low means just a little bit of it does. So this a dissociation equation, you're not looking for high solubility or low solubility. You're telling me, if it split up, what would it split up into? That's the purpose of a dissociation equation. So what I want you to do, way below this, I'm going to do it on the smartboard, but you should have lots of room left on your sheet of paper. Let's look at an ionic compound. So, for example, I'm going to take barium nitrate. Is that okay with you? Let's do barium nitrate. So way down below, let's talk about barium nitrate. What are some things that you know about barium nitrate? It's an ionic compound. How do you know that it's an ionic compound? How do you, yeah, we know for sure that this is ionic because barium is right here. It's on the metal side of the periodic table. So this is made out of positive and negative ions, right? What else do you know about barium nitrate? What's the formula for barium nitrate? It's going to be Ba what? It's Ba2 plus, and also it's made out of NO3 minus, right? So how do we make a compound out of these two things? 1 Ba and 2 NO3s. So the formula is Ba bracket NO3 bracket 2. Okay, no problem. Now what I want to know about this thing is this low solubility or high solubility? Does anybody need to borrow a data book? Yes. Big or small? Are you? Okay. You have a question. What's your question?
Are ionic compounds always solid?
They're always solid, yeah. Like, when I think of a very stereotypical ionic compound, I think of this. So, do you think this arrangement of positive, negative, positive, negative, positive, negative, positive, negative, is this going to seem like it should be a solid at room temperature? Yeah. So, all ionic compounds are solid at room temperature. And then when we dissolve them in water, then something else can happen, whatever. So, is this high solubility or low solubility? It's high solubility. It's got a lot of solubility. So let's think of two totally separate things, okay? Let's think about the major entities for this substance, and then separately, let's think of the dissociation equation. So what are the major entities for barium nitrate? If it's got high solubility, is it going to stay together?
No.
It's going to split up, right? So what are the things that you're going to have in solution? When barium nitrate splits up, you get barium and nitrate and water. So I want to be very clear. When these ions split up, do we get ions out of it? Do we get ions moving around in our water?
Yes.
Yeah, so we should probably have charges. Barium 2 plus, aqueous. We're going to have nitrate, aqueous. And then what do we always have in our mixture of water? Water. H2O liquid. Okay, related to this, but not necessarily the same thing, right? It doesn't matter if it's high solubility or low solubility. When barium nitrate splits up, let's write the dissociation equation. When I say equation, I need a reaction arrow. I need, every time you write a chemical reaction, it has to obey two laws. What are the two laws? Wim, give me one. Conservation of charge. So all the charges on both sides have to be the same. They have to add up to the same total. And then what's our other law? Conservation of matter, conservation of mass, right? So a dissociation equation means when I put this thing in water, we want to see how many and of what things do we get when it splits up. So how many bariums will we get? We will get one barium. And it's an ion, so we will write the charge on the ion. And Cassidy? We're going to get 2 NO3 minuses. Does this chemical reaction follow the law of conservation of mass? Yes. 1 barium, 2 nitrogens, 2 nitrogens, 6 oxygens, 6 oxygens. Yes, it does. Yes, Stephanie.
How do you know that the major entity and the products of the dissociation equation are aqueous?
Because this has high solubility, anything that has high solubility means it was successfully dissolved in water.
Okay.
Anything successfully dissolved in water, we call it aqueous.
Okay.
Yeah. So, so this thing, when it splits up, right, it'll turn into barium 2 plus and 2 nitrates. Hopefully that's there's not a bunch of confusion in here, right? When I put barium nitrate in water, my major entities are barium, nitrate, and water. That's because this thing split up, right? So hopefully there's no confusion on that. Now let's do something that really, really, really kicks people in the groin sometimes, okay? Let's do something that really makes people uncomfortable. We're going to do something similar, but now we're going to talk about calcium carbonate. I want you to do the same thing in your head or on paper that we just did. what do we know about calcium carbonate? Is it ionic? Yes, it is. Calcium's right here, so it is ionic. What's the formula for calcium carbonate? So it's made out of Ca2 plus ions. And if you don't have it memorized, which is totally fine, what is a carbonate ion? CO3 2 minus. So how many calciums and how many carbonates do we need? We need one of each. CaCO3 solid. So if I had calcium carbonate, this is what the formula for calcium carbonate would be. It's a solid ionic compound in its pure form. Now let's do the exact same thing we just did. Let's take a look at the major entities and the dissociation equation for this thing. When I look at the major entities, I have to think about, does this thing actually dissolve in water? Like, does the majority of it dissolve in water? Yes? No? Okay. Most of you are looking at the table and you're saying no. No, it doesn't. This thing is not very soluble. Does that mean absolutely none of it will dissolve? No, it means the vast majority of it, the major entity, remains as a solid. So we say it's insoluble, so the major entity is calcium carbonate solid, right? We just kept it together for major entities. What else do you have in your solution? Or in your mixture, I guess I should say. H2O. Okay, here's the part that makes some people really uncomfortable. A dissociation equation is not asking is it high or low solubility. A dissociation equation is asking if it could split up, what would it split up into? If it could. So our dissociation equation we would start with CaCO3 solid. If it could split up, what would it split up into? It would split up into calcium ions and carbonate ions. Does most of it split up? No, but that doesn't matter for a dissociation equation. The dissociation equation is just asking us, if it did, what would it turn into? How many of these things would we get? Does this chemical reaction obey our law of conservation of mass and our law of conservation of charge? Yes, it does. 1 Ca, 1 Ca, 1 C, 1 C, 3 O's, 3 O's, and both sides add up to a total charge of 0. So hopefully that kind of clears up the difference between the major entities and the dissociation equation. It's a very similar thing for acids, right? Except acids, we don't split them up into low solubility and high solubility. What do we split them up into? Weak and strong, right? Weak acids, can they split up? They can, but do they 100% split up? No. So we will keep them together. Only for major entities. But they still have the ability to split up. So in an ionization equation, remember, an ionization equation is a lot like a dissociation equation. We're just asking ourselves, if it could split up, what would it split up into? Does that make sense? You're not focusing on strong or weak. You're just saying, if it could split up, what would it split up into? A strong acid, are we going to keep it together? No, we're going to split into H plus and whatever is left over. And whatever is left. Hopefully that kind of makes sense. That's all I really wanted to say for our kind of review of major entities and ionization, dissociation, stuff like that. Pardon? Oh, we could totally talk about molecular. Sorry, yes, absolutely. Let's talk about molecular. Molecular is split up into high solubility and low solubility. Okay. What things do you know? Molecular compounds are kind of vague. We haven't done our bonding unit yet, and in the bonding unit, we'll talk about what makes something soluble in water. So right now, we just kind of have to memorize some stuff. What things do you know? What molecular compounds do you know are soluble in water? Wim? Sucrose. So sugars, sucrose, glucose, fructose, dextrose, some maltose, anything like that, okay? So it's just any form of sugars at all. Any sugar and anything else, Cassidy?
Doesn't it have like things that are like alcohol?
Any form of alcohol at all. Not any form of alcohol, not like vodka and rye and bourbon or whatever, but any all. Methanol, ethanol, butanol, whatever, it doesn't matter. So any alcohol, and I'm gonna like put a box around the all because that's how you know it's an alcohol. Any sugar and any alcohol are soluble. Other than that, I'll tell you right now, you're not going to come across anything until the end of the year. If it's anything other than this, for example, like if I said C3H8, is this an all? No, it's propane. Propane isn't an all, and it's not a sugar, right? So it's not going to be soluble. Usually things that are soluble, they have some form of an OH, or they have O's and H's together in them. So that's pretty good for now. I just wanted to focus on that for a little bit because we had an extended class today. And then now we're going to do some other stuff, if that's okay with you. So now I'd like you to take out your 5.3 notes. Take that, squirrel it away somewhere. Tomorrow. Yeah, did I say that yesterday? Yes. Oh, yeah, did you want to go through those questions? Like that we had the answers on them. I totally forgot that we didn't have time to go through them. But I think I did ask yesterday. Sorry, Jenna, I'm going to take this one. I did ask at the end of class, does anybody want me to go through any of these questions? Did you have any questions about any of those questions? No? Okay. All right, that's fine. So we've gone through percent concentration, we've gone through parts per million, we've gone through molar concentration. Now we're at our last little bit of math for this chapter. And it's something that we call the dilution equation. So if you go to, this is the bottom of page 8 or something in your notes. Page 7? Okay, good. No, sorry, we're going to skip, sorry. I'm doing this in a different order this year. We're going to skip concentration of ions, and we're going to go to preparing a standard solution by dilution. That's what we're going to do. So what is this? This is the top of page 10 or something?
Bottom of page 9.
Bottom of page 9? What? I don't know, maybe I inserted it. Whatever, it's all good. Okay, so yesterday we were using a pipette at the end of class, and I don't know, was it pretty easy for you to use a pipette? Yeah, phenomenally easy? We'll see. Okay. Did anybody get water in the bulb yesterday? Yep. Water, it's fine to get water in the bulb, but it's not fine to get like, Kool-Aid or potassium permanganate or copper 2 sulfate or something like that. Okay, so diluting a solution involves taking a concentrated solution. So here we have a concentrated solution, a solution with a relatively high, remember that's all relative, a relatively high concentration. And what we're going to do is we're going to add additional water to it. And so the reason why I wanted you to have your pipette skills is because I want to show you our goal for tomorrow. For tomorrow, you're going to take our concentrated solution here, and you're going to pull up. Do you remember what volume this pipette was? 10 milliliters, right? So you squeeze the bulb, put it lightly. Did anybody jam it on and couldn't get it off yesterday?
Yeah.
So you just lightly press it on. It's slightly, okay? And then you're gonna pull up your solution. Remember, if it's going too fast, you can gently tap it down on the bottom. And like this bulb, you see how fast the water is coming into this thing? That's because it's stuck on the bottom, right? So bring it up above the line and then drop it, okay? So now what I want to do is I want to get this solution to be exactly at that line. I don't know if I was showing people yesterday, I'm not even lifting my finger off the top. All I'm doing is I'm putting less pressure on it. So when I put less pressure on it, it starts to drop and drop and drop, right? I'm not actually taking my finger off, I'm just putting less pressure on it. So what we're going to do is we're going to pull this up and we're going to get it to stop at the line. So I'm just going to do this real quick. Shouldn't take that long. Perfect. Okay, good. So I've got exactly 10 milliliters here. The meniscus is at the bottom of that line. Now what I'm going to do is I'm going to add it to this thing. This thing is called a volumetric flask. I don't know if you can see, but it's basically the exact same thing as a pipette. Okay, I don't know if it's going to focus again. Oh, whatever. Yeah, there you go. But there's one line on that volumetric flask. It's the exact same thing as here. It's calibrated to a very specific volume. This thing is calibrated to 100 milliliters. So I'm going to empty my pipette into here. So I had my concentrated solution. My concentrated solution, 10 milliliters into this volumetric flask. I'm just going to wait for it to empty. There's a tiny little bit of liquid left in there, and that's fine. You're not supposed to push it out with the bulb. This is calibrated so that, yes, there will always be a little bit of liquid left in there. Okay, no problem. So now I've got my solution, and I've got there we go. So now my solution's way down here. How am I going to get the volume all the way up to the top of the line? All I have to do is add water, right? So we're going to add water all the way up until the top of the line. And when we get close to the top of the line, like you will be using distilled water from a water bottle, right? Always, always, always. I'm using tap water because I don't care. And I'm trying to do this as fast as possible. So we're going to add it, blah, 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 blah. Okay, and then once I get even remotely close to it, once I get remotely close to that line, I don't know, can you see how there's a meniscus, there's like a dip in the water level? We only care about the bottom of the dip. That's the point that all of these lines are calibrated to. So what we're going to do is we're going to take like a little eyedropper or a pipette, and we're going to add water until we get exactly to the top of that line. And I should be at eye level. So this is kind of weird, but see, my perspective is a little bit different from yours. I'm exactly at the line. And so it might, no, that's a pretty good perspective. I don't know if you can see, but my meniscus, it's the lens is at a different height, but my meniscus is right at the top of that line. And that's exactly where I want to be. I mean, for the purposes of Chemistry 20, I don't want to say it's okay to be off by a couple drops, because it's never okay to be purposefully off in an experiment. But that's what I expect of you. I expect that line to be exactly at the bottom of your meniscus. Does that make sense? So now all we have to do is cap it. We'll cap it with something else, don't worry. We'll cap it. And then you just invert it 10 times. And that will mix it together. And now all of a sudden I've got a diluted solution. That's the purpose of our lab tomorrow. Tomorrow, and we're going to do this tomorrow. Today we got to get used to the last little bit of math for this chapter before our test, which is going to be next Friday or something like that. Yeah, I think it is next Friday. So we went from a concentrated solution to a dilute solution. Do you see a difference between these? Yes. Hopefully you do. Hopefully. I shouldn't even actually be using that one. I should be using this one. This is the one I took it from. So this is our concentrated solution, and this is our dilute solution. Do you see a really huge difference in the color? Yeah, absolutely. A bigly, hugely, massively difference. Okay. So what we're going to do is we're going to do some math here, and we're going to try and figure out, okay, if this is the final volume I want it to be, what's the starting volume have to be? That kind of thing. So because this process does not change the number of moles, look at this. Did the number of moles of my solute change between here and here? No, I've got 6 dissolved particles, and when I add water, I still have 6 dissolved particles, right? The number of moles doesn't change. And so it's just really the ratio that we're changing. So we've got a calculation for that. It's C1V1 equals C2V2. And it's not in your data booklet, but it's on your magic green, or you can just take it out right now, your magic green sheet or your magic blue sheet. Do you see C1V1 equals C2V2 anywhere on there? It should be down close to the bottom. It's in the solutions part, right? Yeah. Does it say CIVICFVF? Okay. Okay. I can never remember which one it's using. Hopefully you understand. There's no difference, right? CIVI or C1V1 CIVI. What does the I stand for? Initial. What does the F stand for? Fine. Okay. All right. Whatever. It's the same thing. Now I want to be super clear. It doesn't matter what your units are for concentration. What are the 3 types of concentration we've dealt with so far? One type is parts per million. One type is percent. The one type is amount concentration or molar concentration, right? It doesn't matter what you're using, because the unit you start with will be the unit you end with, or the unit you end with will be the unit you start with. You can use parts per million, you can use percent, you can use amount concentration, doesn't matter. Volume is the same thing. For this calculation, if you start with milliliters, you better end with milliliters. So as long as they're the same unit, doesn't really matter, okay? But typically we like to use liters, typically we like to use moles per liter, something like that. Okay, let's try the first example. Water is added to a 0.2 liter solution of 2.4 mole per liter ammonia until the final volume is 1 liter. What will the final concentration be? Okay, the first thing I want to ask you, how much water did we have to add to go from the start to the finish here? Do you recognize how much water did we start with? What's our initial solution volume? 0.2 liters. And what was the final solution volume? 1.0. So how much did we have to add to get from here to here? 0.8 or 800 milliliters. Does that make sense? You're not always adding a liter. You're not adding your final concentration. You're adding the difference between the two, right? Okay, but this question is asking, what will the final concentration be? Now, because this is using a formula, what I like to do, you know me too well. Squiggly line. So what are we doing? Stop me when I get to some pivotal information. Water is added to a, what is that? It's either V1 or VI. What do you want to use? VI. VI is 0.200 liters. Okay, let's keep going. It's a 0.200 liter solution of 2.40 mole per liter. What's that? That's C1 or CI. Doesn't matter what you use as long as you stay consistent. Moles per liter. Until the final volume, well, it's telling you VF is 1.00 liters. And then what will the final concentration be? Let's start with our original equation. CIVI equals CFVF. And what do we want out of here? We want CF. How am I going to get CF by itself? Divide by VF. So CF is CIVI over VF. Does anybody need a calculator? Luke, do you need a calculator? Okay. .200 liters times 2.40 moles per liter divided by 1.000 liters. 0.48. But as long as we keep our significant digits, right? How many significant digits do we need? 3. So 4, 3, 3 makes 3. 0.480. What do you notice about our units? What happens? Liters and liters cancel, and we're left with moles per liter. Do you see how it doesn't matter what units we start with? We'll start with and end with the same units, right? If you start with parts per million here, then you'll end with parts per million. If you start with percent, you'll end with percent, right? So it doesn't matter what units you end up with, whatever you start with. Moles per liter. Good. Do you, like straight out of the gate, do you feel comfortable trying this one on your own?
No.
Okay. Why don't you just try it? Just take 2 minutes. What's the first thing you should do? Then there's questions after that that you can do.
Yeah.
should.
About the same answer, I think.
Yeah. Yeah, my units are wrong, right, for this question? Well, no. I mean, my answers units are wrong. It's saying what volume of hydrochloric acid, so what should our units be? Yeah, it should end up with liters. But what's the initial volume here? We don't know. It says what volume must the student initially start. So that's what we're looking for.
This is from the dentist. I haven't cleaned it. I got rid of most of the garbage.
No, we don't. Yeah, we can start with percentage concentrations. That's the beautiful thing about this equation. It doesn't matter what type of concentration we start with, percents, part per million, or mole per liter. Doesn't matter. You don't have to convert it.
That's why I wasn't doing it.
Oh. So you're just being lazy, right?
Yeah.
Oh, that's a good sign for my Chem 30 student next semester.
I got get these little things like that when I do fashion shows.
Are we good with this interpretation of this question? It says the student was instructed to dilute some concentrated HCl. So we're starting with 36% and we're turning it into 10%. And we want to make a final volume of 4 liters. So it says what volume should we initially start with? So how are we going to get VI? Divide by CI. So VI, CF, VF over CI. We want to finish with 10%, and we want 4 liters, and we're starting with 36%. So what, don't even worry about the number, but what happens to our units? Percent and percent are gone, and we should be left with liters, right? So hopefully you're okay with that. It should be 1.1111111111111, right? But we need to round it to 2 significant digits. So we're going to go 1.1 liters. If you, ooh, man, that's such a good question, Wim. If you told me 1.1, I don't want to do liters yet. If you said 1.1 liters, is that 2 significant digits?
No.
You're telling me that is infinite significant digits. You know what I mean? Like, that's a small, I probably wouldn't mark you wrong for that. But you're telling me by saying 1.1 with a line across it, you're saying, oh yeah, this is an infinitely perfect number, and I'm always going to have infinitely perfect numbers with this particular example. And no, you don't. You know that you want about 10%, so you should be about 1.1 liters. You know what I mean? Yeah. Okay, there's questions here that I would like you to answer. I just want you to do this, and then I'm going to start talking about the lab for tomorrow. You're going to have tons of time to work on the assignment, tons of time to work on the two pre-lab questions for tomorrow, and tons of time to work on a review booklet. So just do these 2 questions for me, and then you can start working on whatever you want. Yes.
But especially cooking books, so they do get very passing out. But this day She's pharmacist, so yeah, she's giving me speech and back to like take it out. She's just it was painful like when they push the fluid in. It's like, or she's like, is it hurt? And I'm like, yeah. And then after like the right issue was like, I'm in my head, and she's like, no, not again. So my body got pinched and she's like, my body like went into like fight or flight mode. It's also just like like it was I was fine. It was sad. It was so like it doesn't even hurt when it sticks in. It hurts. Yeah. So then I got really like sweaty and stuff and like headed. So flu shot. And all of my friends at work are like.
I don't know. Yeah.
My body just doesn't like stuff being put into it, so I'm shut down. But I don't like, this was a 10 minute span.
That's the lowest number you
And I sat there, then I like laid down there. For a good 10 minutes, I was like,
So if you want 10, you
like
can
it
start
looked
with
like I had and then it started to get better. Yeah, it's just draining shots, and then because I have bad reaction.
Yeah.
Yeah, I just
I don't see
I'll do that.
Yep. Yeah. So, okay, so what are your units going to be? So liters and liters cancel out. And then just go 4 times 90. Okay, good.
I don't get how people. Thank you.
I'm not using it for that.
Like, I would not, especially for this one, I put four over the fractions, like this fraction divided by this fraction divided, and it worked every time. And then you don't have to like.
So what?
Fraction.
Yes, because this is 2, 3. Well, that's the fewest, so we need to correct it.
Exactly. I think so.
Yeah.
Probably.
And because we already put in the work of learning Boyle's law, this is sometimes, you know, maybe a question will ask, how many liters of water do you need to be? That's like a weird kind of question that might so yeah. Yeah.
I'm waiting for changing sounds. Why is mine writing?
I have time for work, so I was like wearing it. Like, but and then like she gives a bunch of work back, and she gave me half the amount of work for the month, so I just do all of the assignments with you, and then like kidding about like running fast because I have to do it. But she did like 70
I'm going to give you a minute to finish up those two questions, then we will go over them.
I will switch over the second volume.
I'm having one problem.
It's giving you like an initial.
My problem is not your It's a higher concentration. So there's less water.
So it says calculate. Calculate the volume.
Why don't you just get some ice?
So if it's saying it's the initial, then it's asking what the initial volume is, like paired together. And then it says to make a final volume. So those two are finals, and you're looking for initial. Okay, I'm gonna give you 10 seconds to just finish up. Hopefully you've thought about the questions. Hopefully you've kind of taken a look at them and had a good kind of stab at them. So, the first thing I want to ask you, is in this first the question number 6, is it giving you anything about initial and final something? Yes. Then you know you have to use one of the formulas on our green sheet. That's an important kind of piece of the puzzle to recognize. As soon as you see initial something, final something, then you should go straight to the green sheet. If it's gases, use one of the gas laws. If it's solutions, then we're talking about dilution. So our initial concentration, which one of these is initial concentration? 94%. So we're using percent. Sure, could have used parts per million, could have used moles per liter, but it doesn't really matter. What's our initial volume? 4 liters. And we don't know what the final concentration is, but we want to dilute it to 9 liters. First of all, the thing I want to ask you, how much volume do we need to add to do this dilution? How much volume, how much water do we need to add to perform this dilution? We start with how much? 4, and we go to 9, so we had to add 5, right? Okay. That's just, it's not important for the question, but it's important to keep in mind because I could ask you that. So we're looking for CF. CF is CIVI over VF. So 94% of 4 liters into 9 liters. Hopefully you got 41 point some 7777777. So how many significant digits should we have? 42%. That's we're going to make a final concentration of 42% when we take 4 liters and dilute it into 9 liters. This next question, would you agree? Question number 7 was worded more awkwardly than the first one. Okay, maybe, maybe not. Many solutions are prepared in the lab from purchased concentrated solutions. Calculate the volume of concentrated this much stock solution a lab tech would need to make a blank blank. So we're making something. That means these are finals, right? If we're making it, then that means this is an initial, and we're looking for our initial volume. So CI is 17.8 moles per liter, which is incredibly concentrated, by the way. VI, we don't know. CF, we want 0.200 mole per liter. And VF is 2 liters. So if we're looking for VI is CFVF over CI. So we're going to take our 2 liters, multiply it by 0.200 moles per liter, and divide it by 17.8 moles per liter. What happens to our units? Which units cancel? Moles per liter cancel on both sides. And we'll be left with liters. 0.022. So let's take a bunch of significant digits here. So 0.022. 1 something whatever. It doesn't matter. Okay. So how many significant digits do we need? 3. Here's my 3. And what I would argue to you, what I would kind of propose to you is these 3 digits, do they include the decimal place? Is the decimal place included in these 3 digits? Then probably what do we want to use? Scientific notation. So we will go 2.25 times 10 to the negative 2 liters. Another way of saying this, we could have said 22.5 milliliters is something we could have done. That's totally fine. Doesn't matter. Okay. So